There's the concept that not deploying AI is a risk in and of itself.
Yeah, not using AI, that we're beyond that.
Just a little bit of change can have like a huge impact. Even with global shipping, you can see patterns in weather change. I think we've lost a lot of trust in our society. You know, we've seen so many conflicting statements about everything in the world. That sort of sense of like, this is truth has eroded over time.
With every G, when we developed 5G, we were thinking, okay, what are the leading use cases? How should it be formed? What do we see in the future? So I think in the same way, we're kind of looking for in the next generation. We're looking at 6G.
AI has so much potential. I mean, it's like anything else. We can use it to create amazing things. You know, it can be the nuclear power plant, or it can be the nuclear bomb.
Well, we'll see how different the humanoid patterns will be from humans.
Hey everybody, I'm Chris Brandt, host of IT Visionaries, and today I'm sitting down with Elena Fersman, VP and Head of AI Innovation and Incubation at Ericsson. Welcome to IT Visionaries.
Thank you so much.
Well, thanks for being on. This is going to be a fun conversation because I think people probably need to be reintroduced to all the things that Ericsson's doing, because, you know, I think Ericsson was such a household name for so many years in the early days of the cell phone. But you're doing a lot of different things now. You're not really doing the cell phone thing anymore. So it's interesting to see where you guys are at. You're still in the telecom world and still doing things in that space, but you're a very different company these days. Could you just give me a little bit of like where you've been and what's been going on with Ericsson?
Yeah, it's fun now. We don't make cell phones anymore. We're more like an AI company nowadays, or AI infrastructure company. That's for sure. And digital infrastructure company. Back in the days when I joined the company some 20 years ago, I was actually working on mobile platforms. So the embedded systems, they're actually the platforms that would go into cell phones, not necessarily Ericsson, because we used to deliver to other vendors as well. And just like, and it was great. It's great to work It's great to work with embedded systems, you know, because you have all the electronics there, and it's very resource constrained thing. I like this resource constrained things. Then when you need to apply your algorithms, and they need to be perfect. And then gradually, I think I moved into more end-to-end, you know, network optimization for telecom networks, not only the device, but end-to-end. And of course, you can imagine that AI plays a very big role there, end-to-end.
So I mentioned in the intro about the AI RAN Alliance with T-Mobile and NVIDIA and a whole hostful of other companies. Could you talk a little bit about like what is the AI RAN Alliance?
So the ambition is actually to develop use cases for AI and telecom network symbiosis. Essentially, what you mentioned in the beginning, we are like really looking into AI and telecom network symbiosis. And there are essentially two major parts. So we are looking into AI for networks and networks for AI. And we're talking about RAN. It's a RAN Alliance, Radio Access Network, but we're also looking at it a little bit broader sense, because in RAN itself, you can have AI or whatever algorithm optimizing the embeddings, the deeply embedded part of functionality of the network. And then you can also have more operations and management layer, which is not as time critical, but it's still very important. The cool part of that is that we can actually expose it to developer community, and there can be, well, obviously a bigger scale of developers developing new features that would be controlling radio access network. So that's one part. That's AI for RAN or AI for network. And then, of course, we have the second part, which is network for AI. And that is actually addressing all the new use cases, all the new applications, everything that we see out there in the market, everything, the rise of generative AI, all the large language models, all these use cases. Of course, they need to be distributed at some point. Of course, there needs to be some kind of network component into it. And the network traffic patterns are changing because of these new AI use cases. So that's the second part of the work. So the two parts essentially looking into how to address it, how to make sure that all this, well, in the end, it kind of boils down to what the consumer sees or what the enterprise sees.
Yeah.
If it's smooth enough, if it's working. well enough. So
yeah, I mean, it's very interesting the way you put it. You sort of said network for AI, which is obviously sort of central to making AI work, and then AI for networks. So it's like you're addressing both things. So let me just kind of take those one at a time a little bit here. So network is obviously central to AI, and I think one of the challenges that we're going to face is we're starting to see AI push to the edges a lot now, I think, right?
yeah.
And that makes networks so much more important, right? Could you talk about like what is that AI edge use case and like what is missing from today's infrastructure right now that really needs to be addressed?
Yeah. Yeah. Fun fact, or funny enough, when I work with it, where I'm kind of thinking about next generation of the networks and all this next generation of use cases. So that's how we
Love
develop
that.
every G. So when we develop 5G, we were thinking, oh, okay, what are the leading use cases? How should it be formed? What do we see in the future? So I think in the same way, we're kind of looking for in the next generation. We're looking at 6G and okay. Long story short, when we discuss about augmented reality and mixed reality use cases, for example, to me as a person, I think it's all been done. So it's like, well, it's there, it's out there. So AR, VR, XR is there, but it's not really. It's not because the network's role here is actually to make it at scale. Just to have it in the lab, that's one thing. You can prove, like show a use case where you do some kind of maintenance of a truck or something, of a car. You can go walk inside a nuclear power plant and fix something completely in virtual reality. So that's great. When it's one person or 10 persons and you can render it perfectly and everything. As soon as we want to offer it at scale to the consumers, then we are in trouble because we need to have more capacity and we need to have more optimization on the algorithms. So that's kind of the biggest thing. Then, I mean, while mentioning AR, VR, this is kind of a very given obvious thing when we need to have edge offloading when we are at scale, because when you have your goggles, there's a lot of AI processing because you have a video feed and then you need to process that video feed. So how much do you send and where do you have the AI algorithm? Maybe you don't want to run around with a backpack of GPUs, right? So you want to offload it somewhere.
Yeah, and you want to have low enough latency that you're not nauseous the whole time you're doing this.
You don't want to be nauseous, exactly. And then maybe some other extremely real time or time critical use cases, safety critical use cases where, well, people do remote surgery, for example, through telecom networks. And when you are, and then people asking me questions, who would like to go for remote surgery? Maybe you don't have a choice. Maybe you're somewhere in rural place where you don't have a doctor and you need to have someone who would be operating on you. So this is when the latency is extremely important.
Yeah. Well, and I think people don't really understand the difference between all of the G's, as you call them.
Yeah.
We've had 5G, 5GE on our phones, and everybody's like, oh wow, I've got a 5G phone, right? But that's not really 5G, right? And now you're sort of talking about 6G, but you're talking about an enormous explosion of capabilities here. I mean, the difference between, like the 4G networks and a 5G network is massive. And I got to imagine, similarly for a 6G network, but there's a lot of use cases that get wrapped up in all of this stuff that specifically kind of work towards that network for AI that you talk about. I mean, the 5G where I see it being deployed heavily right now is more in like warehouses and factory floors and things like that seem to be like a really great use case for it. And that's another spot where we're starting to see this real growth of AI in that space as well. I mean, like, can you talk and without missing one of the biggest AI implementations, obviously, is automotive and sort of that car communications was very different than a factory floor kind of communication. Could you talk about like how the network becomes such an integral part to this world of AI?
Yeah, absolutely. So to me, 5G, this is how we kind of positioned the 5G back in the days when we were still doing it, research on it. It's essentially, I mean, from 4G to 5G for consumer, maybe you don't see a huge step because 4G is actually enough for all the consumer related communication when you're making a call or you're texting, you're sending a video feed, you're making a video call. So when it popped up, the 5G symbol, people are kind of like, okay, so what? So what? Because 5G is really a network for industries. And it's one network that allows differentiated connectivity for industries. It has a concept of network slicing. So this is where we're talking about 5G standalone when the 5G core can allow this network slicing for the industries. And the cool part about network slicing is that it's a virtualized network. So it's almost like a virtual machine. When you request a virtual machine, it feels like your dedicated hardware, but in practice, it's a virtualized slice of a machine, of a compute. In the similar way, we can like create a virtual network, virtual network slice that looks and feels as if it's your own slice, and you can have your characteristics, and the characteristics can be completely different. So on the factory floor, you can imagine when you have, for example, heavy machinery, remote control heavy machinery. When you remote control heavy machinery, one of the most important things is high bandwidth uplink,
Right.
because you want to send it, and very low latency because you want it to be precise to control it. So that's one slice. In the factory, you can have one slice only for your heavy machinery. And then another slice would be maybe for sensors and actuators that just monitoring everything. And that's completely, it's not at all as critical, as timing critical. That's a different slice. And that's cheaper because it doesn't require so much bandwidth. It's just a little data. Little data is also important. And there could be agriculture use cases that are just monitoring, but then you need to have a very long battery life because you don't want to change the battery in your devices. So that's really all the variety of use cases. So the coolness of this differentiated connectivity in 5G is that you can configure your virtual network exactly according to what you need.
Well, and I got to imagine, because like you talk about like receiving telemetry from factory floor machines and then also at the same time feeding that back into an AI or a remote, control system or even like safety systems that have to respond very quickly and things like that. Right.
Yeah.
I mean, so you're using one flavor of 5G for, a part of it, sort of that low bandwidth kind of telemetry piece, or it could even be high bandwidth too, but, and then that ultra low latency, high bandwidth kind of thing. And I got to imagine that you necessarily are going to have some variability to all that. And that's got to be kind of real time in the moment in response to certain conditions, which then gets into that sort of network AI for the network piece of it too, right? Because now you're looking at like, okay, I've got this technology with all these capabilities and these, the requirements around that network might change from second to second. And you need to have something that's going to kind of dynamically adapt to what's happening. And that's where you're going to get the real value out of 5G and I imagine 6G, right? So what do you see coming on the AI for the network side of things?
Yeah, so AI for the network side, if I would kind of simplify it a lot, then I would say AI is there. We need AI because networks are not perfect and they will never be perfect because we live in the real world.
Right.
If we had unlimited electricity, unlimited CO2, we had unlimited capacity, unlimited bandwidth, we don't need to optimize anything and we don't need AI, roughly speaking. But in reality, we only have this much space on the planet and we have this much space where we can install the base stations and antennas. We can only burn as much electricity, well, as little as possible. We're trying, right? We're optimizing that, and we want to have certain performance for certain industries. So, roughly speaking, AI is there to optimize imperfections and to optimize the utilization. So roughly speaking is, since the network signals won't be perfect and we want to predict that anything fails, we want to predict the signal degradation. We want to be able to predict that a generator will maybe malfunction. We want to predict that, well, in some cases we cannot predict. In some cases, there are simply, birds that would be, ruining the antennas because they build their nests there.
Sure.
In some countries, and there are monkeys ruining the antennas, and there are some things they chew on, and maybe you cannot predict, but maybe you can if you send a drone and in advance.
Squirrels are particularly bad for networks. I've found they like to chew through cables all the time.
They like something in the cables, exactly.
Yeah, there's something about it.
Yeah, something yummy there.
Yeah.
So essentially, all these predictions, and that's very interesting because, like, when you kind of sense. Normally we collect the data. We don't need to collect a lot of data. We just monitor everything that a network is functioning as it should. But in certain cases, there are some triggers. And we detected, for example, we had a case where we detect quality of experience degradation. And actually, in some cases, it's enough. You can detect it like 9 minutes in advance. So 9 minutes is plenty of time. It's oceans of time. So you can do a lot. And of course, you can prevent most of the problems. You can prevent by software upgrade or fall over to a different system and so on. So this is where AI plays a big role. But that's not only it. That's not
right.
So obviously utilization of infrastructure, so that we, with our installed base, when we install certain amount of infrastructure, we get the most out of it. Best coverage, so that signals don't so that they don't interfere with each other, so that they propagate in the best possible way, so that they cover as much space as possible. We need to predict the mobility, how the people moving in the cities, and we are following that with the signals so that they cover as much as possible. So that's one. So then of course, energy consumption is another big one. Performance, so that performance is just enough, right? So maybe you don't want to put huge amount of resources where you don't need them. You want to put resources when you need them. So all these types of optimizations. But then, of course, AI also opens up for new values. So as I mentioned, we can provide APIs to developers, to the network, and the developers can build new applications, and that opens up for new values for sure.
Yeah, I mean, I find cellular networks, for one, really fascinating because there's so much complexity there that I don't think people really understand. I mean, the fact that you can drive literally across the United States while you're playing, music on your phone and talking to somebody on a video call, even while you go, this great distance. And we know that radio signals are limited, certainly to the horizon, in most cases, but, but even smaller regions than that. So there's a lot of switching and dynamic configuration and things that are happening. And I got to imagine there's a tremendous amount of optimization that has to happen here. So I imagine you're utilizing AI for that, but there's got to be more even you can do in sort of like dynamically kind of rapidly configuring this. You talk about failovers and, sort of troubleshooting issues and things like that. I got to imagine all that kind of plays into all this. How are you guys addressing some of those challenges?
Essentially, we implemented these type of optimizations in every part of the network. So roughly speaking, we have radio access network, transport, and core parts of the networks. Then the OSS, BSS piece that is controlling it, and then we have the managed services controlling all of it, all the networks. These smooth handovers that you're talking about, that are even more important for some cases where, well, as I mentioned, if you have remote control surgery, you don't want to drop like a service drop there. It's in the middle. So yeah, there is a predicted handovers we trace, for example, where mobility. Where some person is moving, essentially, you can predict the trajectory. You can predict in advance when the handover need to happen, and there are handovers happening all the time, obviously, because we're handing over from cell to cell. Optimization of link adaptation, for example, the signal strength optimization of any type of performance. We call it quality of experience. So because
I like
electronics
that.
experience is a compound kind of factor
Yeah.
that says like, okay, your quality of experience is manageable, and there is a lot of measurements, essentially measuring what is okay for a person or for a service, perceived experience.
Yeah. So, on that front, I mean, obviously you do a lot more than just sort of manage, like handoffs and things like that. I mean, you're getting deeper into the AI stack there. And I know that like you're looking into the idea of like cognitive networks, this sort of
Yeah.
self-organization of networks. And I know one of the big capabilities that was discussed in the 5G networks was sort of the multi-hop sort of protocols and more mesh-based networks and things like that. And for a network engineer to sit down and try to like build that's got to be very difficult. So like, how do you build a self-organizing network, and like what kind of AI intelligence goes into that?
Yeah, so when we talk about cognitive networks, and we also talk about intent-based automation, and we talk about autonomous networks, a dear child has many names, as we say in Sweden.
Sure.
It essentially works like this. So when we say intent-based, and essentially it's not like I want to talk to the network. I just want a network to be able to address any kind of imperfections by itself. But in some cases, you want to be able to dictate some kind of intent, and that's normally
You want to
business
describe
intent.
the experience you're looking for, right?
Right, exactly, on a very high level, on a business, on the business level. Maybe that's an intent to, get some revenue out of the consumer. So maybe the intent is to decrease CO2 emissions. So
Yeah.
there are different ones. And that intent is being translated. So we have capabilities to translate that intent into the technical nodes. So, and that's kind of almost similar. I can draw similarities to like home automation. I want to improve my whatever ambience in my place, and that means like this lamp do that, this lamp do that, this sound do that, this sound do that, and then I come home and it's like perfect atmosphere there. In the same way, so when we did like ask for a certain business intent on a high level, it goes into knowledge base, it's being decomposed in a smaller intents. Okay, what does it mean? And how can we achieve it? And we can achieve it in different ways. But in the end, it translates to separate technical intents or like much more lower level intents for different nodes in the networks. And that goes, then we kind of execute that on the network functions. On each separate network functions, they will have to adjust in a certain way so that end to end it responds to the overall intent. But that can be, as you say, when we look at, for example, data mesh and the mesh of compute and network, it can translate into this network links being adjusted, the compute links being adjusted, what services being executed where, and so on. So that's essentially the decomposition of that high level intent. But that can be it, and it's not like we're talking to the network. It's always some kind of characteristics it needs to adhere to it all the time. So in practice, it looks like this. So autonomous networks, when it's an autonomous network, it's like an autonomous car. I don't want to tell it. I just say, drive me home, and then it drives me home. So in the same way, it would be like, okay, how am I doing? I'm still executing my intent. I'm kind of minimizing. During 2026, I want to minimize my CO2 emissions. How do I do it? Step by step. This node do that. This node sleep. Also very common technique, which is not rocket science, just to predict how the network in certain parts will be used and then power down certain parts. That's a very simple technique. It's also used on the device as well. And that's something that you start executing, and then you learn. You have your AI model. You know how the user is kind of using the device, or how the service is using the network, and then we just power down parts of it so that we save energy without affecting the perceived performance.
Yeah, I mean, we've spent a lot of time talking about software defined networking and things like that. But I mean, this is sort of taking it to the next level, right? I mean, can you talk about?
Mm.
I mean, like software defined is going to be you're going to kind of have to figure everything out in advance and then hope it all falls into that bucket. But
Yeah.
this is very different. Can you talk about like the difference between SDN and sort of these cognitive networks?
Yeah, I think you said it.
Yeah.
Software defined is so you've defined how it should function, and you can go and tweak it, and then it functions. But cognitive, it's more like it's adjusting over time. So network conditions change. For example, the network, I don't know, weather conditions can change, and then
Right.
we want the network to be able to adjust to the new weather conditions. And well, if there's a storm, it will have to change some characteristics, some parameters. I don't want there to dictate it necessarily. I want the network to see, okay, there is some condition changing. I better start preparing and changing my network. So that's, I think, the biggest learning.
Yeah.
It's learning by itself. It's like acting as the persona and adjusting.
Yeah, and it seems like I think we've seen this sort of on the compute side, with like Kubernetes and things like that, and just sort of like these sort of microservices.
Yeah.
Like networking can kind of become like that too. I imagine, like now we're looking at sort of radio communications and all and wired and all those things kind of interacting and combined together, and like pulling up nodes. And I love the idea of what you're talking about. Optimizing the energy usage of all of this, because as you mentioned, like some parts of this network may be operating with very low power, and some with higher power, but like also, the amount of power we're consuming across the globe, and sort of the constraints we're starting to hit on energy utilization and things like that. I think the ability to optimize those things are really interesting. Do you have any stories about like kind of interesting kind of use cases that you've done around any of that sort of thing?
Um,
And if
we've,
not,
we've
we
done
can skip it.
plenty.
Yeah,
We've
I'm sure
done
you've done.
plenty.
Yeah.
Specifically energy optimization in RAN. I think we are saving 15% just by smart power saving mode, essentially, in radio access network. We experimented with that with a customer in Asia. But that's, I mean, this is how we work. Essentially, we try with one customer, and if it works out, then we will kind of deploy this model and the algorithm to other customers, essentially, and that shows really good savings because. Simply by experimenting and predicting, so predicting the usage patterns. When
Yeah.
you predict the usage patterns and you follow that usage pattern curve, then you can apply this smart power saving mode just by shutting down certain nodes, not the whole thing, but just optimizing that. And that sounds simple. I mean, and it is actually. It's not
once you have AI doing it all for you, but that's simple.
We have AI doing that, and the beauty of it is that if we're saving 50%, 15% in year to 2025, it will be even better the year after. So we'll see even better savings in 2026 because the AI algorithm will learn and will become more precise.
Have you seen, like you mentioned, how it's like it's learning, it's optimizing, it's sort of scaling differently, and I think that scale is a big part of this too. But I mean, do you see is there any kind of cases where you've seen like really unexpected benefits out of some of the things you've done with AI in the network?
Well, I have a case. I have one interesting case. It's been a while ago we've done it, but maybe not necessarily directly AI, but just optimization. Well, there was some AI in there, but it's like not super advanced, to be honest. Back
Well, it
in
doesn't
the
have to be.
days.
That's the beauty. It doesn't have to be, right?
It's the beauty of it, exactly. So we were working with a logistic company, Maersk, and they essentially we were delivering a service, just a communication service to them, so that captains on these boats would be able to communicate with the control centers. But then, obviously, as soon as you start communicating, you have this link and you can trace it. Then you can also optimize the routes. of the ships. And then we could see, I mean, they saw savings, like 20% of savings on fuel, which is fantastic.
Yeah, that's huge.
So that's kind of a side effect of just establishing a link.
Yeah, I mean, with Maersk, it's like just a little bit of change can have like a huge impact. Because I mean, like,
Yeah.
you're talking about like global shipping and things like that. And I know that like even with global shipping, you can see patterns in weather change literally, from all the, shipping traffic that goes through. So 20% savings there, you're talking about an enormous savings, really.
It's enormous saving. Yes.
Yeah.
Yes.
It's not just like 20% off your bill. It's at the restaurant, like, or 20% tip. This is like, you're talking, and this is where that scale piece is really interesting. That you can do these things at scale like that. It's, small changes have a huge impact at scale.
Yeah, that's for sure.
I'm very, very fascinated by things at scale because oftentimes things that seem obvious at a small scale become completely inverted at large scale, and the priorities at a large scale are very different than what you as an individual might see happening. Yeah. Could you talk about like what sort of separates these AI projects that scale from the ones that really don't?
What separates? It's very simple, actually. What separates those that work, I mean, it's like obviously a huge cost. If it doesn't work, then you need to retrain the model every time.
Right.
And this is not perfect. Could still be worth it. But just maybe a couple of examples. If we test some algorithm and perfect it, we have a perfect model, for example, on a small European operator, maybe a small Swedish operator, which is great because like small operators, we can easily, get all the data and you train it and so on, and you get this perfect model. And then you go and deploy it with a big American operator and it doesn't work out of the box. You need to adjust, you need to retrain, you need to fine tune, not to retrain. Fine tune, really. And then the question is always, okay, so we are so happy we have 90% precision with a small European operator. We move it to a different market, and that gives us 70% precision, 60. Where is good? So then the question is like, what is worth? Is it worth it to fine tune, or should we train it from scratch on a certain market, just as an example? And then, of course, you understand that it's to make it work well, you really need to have representative data. So you need to have all the corner cases, you need to have all the markets, you need to have those markets, I don't know, in Africa, for example, where you have completely different weather conditions. And you have those, Nordic countries, and you have those countries that have certain scale of the nodes and a certain kind of layout of the network. So where am I getting? I'm getting at to me. I've seen those cases where you build something and then you this is my perfect model. Here you go, and it doesn't work. So to build the perfect model, if it doesn't work there, then it's not perfect, right? So you want to have the model that's been trained on representative data, and you need to have data from essentially different conditions. And then after you've trained and have all the corner cases, then it will be working. Then it will be like generic enough so that you don't need to retrain it. You can fine tune it a little bit.
Yeah. I'm going to throw a little bit of a wild card in here because I saw something just recently that I believe it was a Swedish company that was doing something really interesting. They were managing the high voltage power distribution lines, and they have a drone that is capable of sitting on top of the cable and through magnetic induction charging the drone. And then so basically you could keep the drone up and running indefinitely, essentially. And there's intercommunication between the drones and things like that, which I thought was really, really fascinating. They just sort of, and their purpose is to sort of continually check the high voltage lines as it goes across. and this is where my off the wall question comes in. I imagine the thing that's interesting about that is like the ability to do something like that, to like kind of keep charging in the field and keep running and have a communication device. Because, when we talk about these, dynamic adapting networks and the cellular networks, we've always been thinking of cellular networks as sort of static, fixed points of radio antennas and things like that. But do you see any innovations coming, from that side of it, where like the network itself gets portable, mobile, and, like through the use of AI, you talk about sort of, these cognitive networks sort of self-organizing from a, routing and communications perspective. But could you also envision a future where you're utilizing AI to sort of move, assets around to, like compensate for weather conditions? It's like you getting a lot of radio interference from, humid and wet conditions, and you add more nodes to sort of distribute more load, things like that. Is that something that you guys are looking at?
Do you want to fly in a base station to follow you? Well, we have discussed
you have that
to have to have your own base station following you on the drone. Of course, no, we don't have that as a product.
Oh, okay.
We have discussed that that's a possibility for sure. I think the way it's solved now, it's more you can move around a compute on top of the network and the power of the link through software. Essentially, that's how we do it. So that's how we're doing it. But having said that, of course, that's completely possible. What you're saying about the drone, and of course, it has communication capability in itself. But it's more like if we want to add portable, base stations moving around, yes. And then we have different products for enterprises as well, which is part of our enterprise wireless solution portfolio, where you can have smaller base stations and you can have, radio dots and so on. So like enhance your telecom network, maybe not as flexible as flying it like, on demand base station, but that's It's not impossible. It's possible to do for sure.
Well, and I would imagine you're probably doing that, and like robotics is a big and emerging thing right now.
Yeah.
And the robots have to be equipped with 5G, 6G too. And
Absolutely.
You got multi-mesh networks and multi-hop networks. So like in essence, you could be, like doing that kind of dynamic configuration of a network for resource allocation and utilization in that regard too, right?
Absolutely. And it's in a way similar to this network for AI kind of, because the physical AI will also play extremely important role in the future. So all the humanoids that we will see in the future, they will need to be acting based on the cellular network and very, precise, in a very precise way. We'll see how different the humanoid patterns will be from humans, though. Maybe they're quite similar. Well, some bigger streams of data for sure they will need.
Yeah, for sure. Sorry for throwing you like a random weird question there.
No, it's great. It's great. I can actually tell a story about the drones.
So cool.
I'm a big fan. So at Ericsson, we were always, since I've been working at Ericsson Research, and we are kind of always experimenting as like challenges. And then when you go into like our managed services, which is our organization running telecom networks on behalf of telecom operators. We have a certain structure. So you have, first line support, second line support, you have back office, and then you have field services. And then when you go into fully autonomous networks, essentially we're trying to automate as much as possible because, humans are great, but maybe we don't need to have like an army of humans like sitting there pushing button, because algorithms are really good at that. The trickiest part to automate there is in the field, where something goes wrong. Because of their weather conditions, because of that squirrels. But so how do you automate? Of course, you can automate through robotics. Of course, you can automate through drones. You can send a drone with a screwdriver. You can repair. You can do all the kinds of maintenance. So there's a lot of activity, just to see what's wrong, what's broken, how we can repair using drones. There's a lot of things happening there.
You're so in the middle of such a cool industry and things that are
I
happening
know.
and moving so fast. What do you say to the CIOs out there that are like, trying to figure out their AI journey? And I think, there's the concept that, like, not deploying AI is a risk in and of itself now. I think we've kind of evolved to that point where
Yeah.
everybody has to really be thinking about this. What would you say to, like, sort of cautious IT leaders and, like, what they're missing and how they should approach this?
Yeah, not using AI. That we're beyond that. I think there is an understanding. We need to use AI. It's almost like not teaching your kid to help you in the kitchen. Just because it's dangerous.
Oh, you
Like,
can teach
no,
your
we
kid.
start.
You can teach your kid to help you in the kitchen. My kids
Well,
went to Montessori and they had all that practical learning experience stuff. I still can't get them to help out in the kitchen.
that's I'm a theoretician there.
Yeah.
But I would say what I saw years, I mean, a couple of years, not a couple of years, 10 years ago, I think when like the realization came there, like, okay, we need to deploy AI. And even at Ericsson, I think where we started, of course, I was very pragmatic where we started. We started with, we started actually with our services organizations because it's easier. It's easier to get there, right? So you have the data is exposed. It's much easier. I always compare it to a human body. So when you have a symptom, you kind of like you have something on your like, I don't know, on the surface that's hurting, and then you go and fix it because it's easy. But then if it's your heart or somewhere, you don't even know the root cause. So the heart would be the radio access network, and that's a tricky one. So uh, and just before jumping on it and saying like, oh, we're gonna uh, deploy these algorithms, or we're gonna I don't know, partner up with this company, gonna do this AI for us. It's not the algorithm that's the starting point. It's getting your data in order,
Mm,
getting the data, getting the right data, getting the representative data, getting the stream of data, not too much, just clean. So all these things. So compared to, I mean, we are an old company, 150 years. So
yeah.
obviously we are not a digital native in the same way as younger companies are. That when they build it from scratch, so that you can read, you have full observability. Of course, we have to transform everything just to be able to observe everything we see. So that would be, unfortunately, my recommendation, which is boring, but this is the reality. Unless you have your data management in order and you have your house in order, it's clean, and you see all of it, then you can pick this algorithm. You don't like it, throw it away. Pick this algorithm, try this and that. You can be so flexible. And I think that would be like, first, get the data management in order. That's very important. The
Yeah.
second one would be make it so flexible so that you can grab anything on the market and deploy it within a week. Because things are moving so fast in AI. I'm so fascinated because, if you remember, there was, when we saw LLMs, the rise of LLMs, and then you have a rise of distilled models, and they perform almost at the same level. And then,
Yeah.
there was a company announcing their distilled model performing perfectly, and then in a week from there, I think there were students from Berkeley showed the same performance on extremely tiny model, and
Yeah.
then there were students from Stanford showing the same thing. So it's moving so fast. So what I'm kind of thinking for companies, it's important to be able to have this like housing or MLOps in order, so you can just grab a new model when it comes out, because it's so fast. It's moving so fast.
It is moving incredibly fast. And I think that's one place where I think a lot of IT folks are struggling a lot because, they start looking at something and then like literally it could be in 15 minutes, your
Yeah.
foundational
Mm-hmm.
model you're using starts to change and do something different.
Yes.
I mean,
Yeah.
it's wild. And I think that is maybe a little, people perceive that as a little bit of a deterrent, but I think, like you say, you kind of get into the game a little bit and start to understand it. And organizing your data is such a really interesting starting point for that. And would you say that, like certainly you got to get your data organized, you got to get it tagged correctly, you got to
Yeah.
normalize that data and all those
Mhm.
kinds of things, and you store it somewhere where it's going to be accessible and available and performant at the
And it's
level you need,
fresh.
and it's
Making sure it's
fresh.
fresh. Yeah,
Well,
exactly.
and that's a really hard problem for AI. And I think, 5 years ago, nobody was talking about LLMs except a
Mm.
small handful of people. But
Yeah.
now that's all people want to talk about. So they're relatively new, and a lot of the sort of foundational models that we are using are based on kind of the same data sets that are used to train them.
Yeah.
But at some point, things evolve, things change, and those foundational models have to be, continually updated and pruned. And
Mm.
I think that's ultimately going to be a bigger challenge than people are really appreciating right now. I mean, what's your
Mm.
thoughts on like keeping your data relevant and useful over time?
Yeah. No, I agree. It's important. Of course, there are some techniques so you can kind of freshen up your model. You have the RAG solutions. Then you can ingest the context of today. This is how it looks today. But just to update them, keeping them up to date. That's a tricky problem. I think it is. And I mean, maybe we can divide and conquer. Because there are some models, there is some data that maybe doesn't get outdated so fast, and then you
Right.
can have those more, models where you don't need to train too often. But then you have like, well, in the end, we will end up with some kind of combination of different models where you have different, well, different kind of data, and some models will have to be retrained much more often and injected with the new data and so on.
I like what you're saying about sort of these distilled models where you're sort of, and maybe you could kind of explain the difference between sort of these really big LLMs that we're talking about and kind of distilled models and how you go from one to the other.
Well, the main difference essentially is that you have less data, but it's still representative. So you kind of remove parts of the model that's like less relevant. So you have you kind of compress you compress it, and out of that like it's almost like compression of a picture. When you see a picture, sometimes you compress it and you don't even notice with your eye. So in the same way, the models can be compressed so that only representative parts of the model are there, the most important things. So that's one very powerful technique of making models smaller. And the second one that I mentioned is that, of course, we can have very specific domain-specific models that are like combined with a big model. Like for example, we've been working with different models for telecom, obviously, and even language models. You can build small models just for specific domain, and it speaks like Ericsson engineer. I mean, it doesn't write any poems. It's very dry.
Yeah.
But it's very precise.
I know. Come on, I'm sure your Ericsson engineers can write poems.
Yeah, well, specific. Yes, I'm sure you're right.
It might be a little dull, maybe around the edges, but yeah.
Well, more fun if you like that type of poetry.
True.
But that's the thing. I think like when your world, if your world is specific generation of packet core, then you will have the model describing your world perfectly. And that's the only thing that you need. If you're there to, go and repair or troubleshoot that generation of packet core, then it's enough for you. But then if you're looking at the bigger picture, maybe you have the full network, then you need to look into different domains. You look into the domain of core, you look into the domain of RAN and transport, and then you connect them and try to navigate. But in the end, probably, smaller distilled domain-specific models that will be very efficient, timing-wise and energy efficiency-wise.
Yeah, and I when you look at the LLMs, there's a lot of like edge case, kind of connectivity in those LLMs, and I think I could even. It makes sense to me that some of these distilled models perform so well because there's maybe redundant data in there or data that is such an edge use case that is not necessarily relevant, and it could even lead to the potential of increasing the amount of hallucinations that you would get in a model, whereas a distilled model would be more focused in some regards. So maybe it wouldn't pick up really weird cases
Mm.
Like it wouldn't be useful in those sort of scenarios, but it would be more useful in like 99.99% of everything in that
Yeah.
regard. Yeah.
And then the model can also, of course, it does give you the certainty. It
Yeah.
responds with the certainty, and then you, as a, I don't know, whoever manages the telecom network, will decide: is it good enough for me? Do I trust it, or do I need to, go with a bigger model? And you can
Yeah.
go and ask an expert who's not distilled.
Yeah, and I love that idea, and sort of at the time of just sort of distilling the model, sort of injecting newer and fresher data, or pruning old data while you're doing those distillations. I
Yeah.
think that's really interesting. Necessarily around that, you would have to have some sort of interagentic communication and things like that happening, and that kind of comes back around to that network for AI that you talked about
Yes.
before. Where do you envision sort of that kind of AI network communication with those kind of more specialized distilled models, large language models, and sort of like RAG-based models and all that stuff, and you have to have some intelligence to sort of direct how those are used and what gets used and things like that, and all that has to communicate. I mean, what do you need? How do you see all that happening?
I think it's pretty straightforward.
It is?
Yes,
It seems complicated to me. Okay.
it's clear as mud.
Clear as mud. Okay.
So on the network side, we
Yeah.
start the network side. We do have a lot of telecom related AI agents, and we do have a lot of different models that we are using. So that's one side of story. So within a network, there are models and agents optimizing the network all the time. So that's one. The other part of story is those big models or models of different sizes that are utilizing the network. I think it really depends on the application. In my world, we need to just be able to be so flexible, so we can utilize essentially any model. So within Ericsson, also when we optimize the network, we can pick and choose. I mean, we support any hyperscaler, we support any different types of models. That's what I was saying. Like as long as you have your data in order, you have organized everything, you can pick and choose essentially. And then of course we have our preferred partners and everything that we work with. But technically, through these interfaces, through the A2A MCP protocols, you can connect any agents because, I mean, we kind of, we live interoperability. When we live,
Yeah.
standards. We
Yeah.
love
Yeah.
standards. That's how we live. That's how we work. So that's
Yeah.
in the end, it's like as long as it's standardized. That's why I said like it's straightforward. As long as there is
Yeah.
a standard, we are fine with it. We can use any agent, and we can interact with any agent, and we can interact with any model because they're standardized.
Well, I got to mention though, like security probably is like it gets to be a little bit trickier in sort of like this, where you're dealing with all these different things that have access to different things, and like
Yeah.
how do you envision that playing out?
Yeah, of course. I didn't mention that because it's kind of, yeah, of course, totally obvious. Like this is one of the
Yeah.
key points for telecom communication in general. I mean, like we
Right.
always say, like quality of experience, real time, mission critical use cases, and then security is always there, of course, as a like key point because it's
Yeah.
the
When it's
networks
coming
need to
over a
be.
radio frequency, it makes it
Yeah.
more of an issue because it's accessible to anybody eavesdropping
Yeah,
and things like that
yeah,
too, right?
exactly. So that's a key point. And then of course, we want to connect our security framework into, it propagates into any model that we are using, right? So you take a model, you plug in and start using it, but how do you know if it's safe, right, and secure,
Right.
right? So that's your question, right? Yeah. Yes, it's something that is being looked into continuously. Of course, you can solve it in a different way, in different ways. Of course, you can write contracts with whichever company who is supplying a model and saying like, okay, if it misbehaves, that's your problem. But if in the end, the network will be blamed anyway, because if
network
something
always
fails,
gets blamed. I used to
yes.
I used to be a network engineer, so I know network is the first place everybody goes.
Everyone kind of recollects there's a network there when it doesn't work.
Yeah, right.
When it just works, it works.
The best day for a network engineer is when nobody complains about anything. That's the good day.
Exactly. So so we have our trustworthy AI framework and trustworthy AI research, and every kind of new tooling that we are adding into our portfolio, or we have a supplier with a model that we're using in our portfolio is being checked, and we have a trustworthy AI research that's been running for 15 years. That's kind of make sure algorithmically that the models guarantee and adhere to certain principles. So, but this is always a moving target. We know that. So security and trustworthiness of AI will be a moving target. We will be keep developing. Someone is developing a model or something. We need to develop some algorithms that verify that there is no hallucination, there is no misbehaving. And there will be. Of course, there will be at some point. It's just we need to make sure that the positives are much bigger than the negatives. But then, now and then, there will be cases that there is not perfect. But as long as you have the guardrail, so for example, if we have a certain algorithm, and we have a lot of those, algorithms that have been hard coded, for many years, and we're running pretty well for many years, but they only operate in a certain, specific domain. So they optimize a channel, for example. Maybe they optimize the channel quality, or they may optimize the electromagnetic tilt of the antennas. So when you replace that hard-coded algorithm with a model, maybe it's not perfect. Maybe it's not perfect from day one. So that's like a child in the kitchen. You need to educate. Like, okay, right. Day one, that's crap. Day two, a little bit better, and so on. So and then like at some point, it will be hopefully, much better performance, and that is improving and learning all the time over time. But there will be situations when it's not perfect.
Well, and I think that's because you're talking about complex dynamic networks with complex dynamic applications and agents running behind there. And I got to mention, and to some extent with some of these things, that the security is going to sort of travel with the agent to some extent. And you have to figure out what can that agent talk to. It's like, I mean, I guess it's no different than having users on your network and doing the same things that you do for all humans. You just have to apply that to AI, right? So it's something you have
privacy.
done.
Yeah, access rights and privacy, of course. Yeah, you're right. Agents will have their own levels of privacy and access control.
Yeah, it's interesting. Well, you've been at Ericsson for 20 plus years, and you've been doing AI for quite a while now. And I know you're extremely well versed in the whole thing, because you have confessions of an AI brain too, right?
Yes.
Could you talk about what are the confessions of an AI brain, and like how you've seen all of this evolve over the last 20 years?
Yeah, so that's a book that I wrote with my co-authors, and the idea behind so the book is a couple of years old now.
That could be 1,000 years in AI time, right?
Exactly. So we had second revision is coming out, actually, because it's moving fast.
I'm sure.
Yeah, it came out just at the same time OpenAI released ChatGPT, so that was perfect. So the idea behind the book is that there is so much kind of I felt a little uneasy feeling that all the books about AI were negative. So there was a lot of, catastrophic books about AI who educate the reader on AI in a way of describing a catastrophic future for humanity. Yeah. And I know that those sell really well because people love fear. People love fear and the catastrophic future.
Yeah.
So I felt it's unfair to a technology called AI because it's such a great technology, and there are so many positives about this technology. So I felt like it's time to give the world a positive way of describing AI and all the good stuff that it
Yeah.
can achieve. And then, of course, there is a chapter of, how not to become a criminal. So it's like describing, the AI as a persona, and from the first person narrative saying like, okay, now I'm in the world of humans, and now I'm doing that, and I'm learning this, and I'm learning that. And of course, at some point, it wants to misbehave like a child, doing something silly or doing something wrong. And how do we make sure not that it doesn't misbehave, and what it can do well and what it cannot, and so on. So that's just a kind of factual, correct, and fully covering educational book about AI, written in a fun way,
I love
kind
that
of positive, in a positive way.
Yeah. There's not enough, because AI has so much potential. I mean, it's like anything else. We can use it to create amazing things. It can be the nuclear power plant, or it can be the nuclear bomb. And it's kind of what we choose. We can make I always keep saying we can make our own hell, or we can make our own heaven. It's like what we choose to do. And unfortunately, our human instincts aren't always well directed. So like I almost feel like we need AI to give us better judgment, to make that beautiful future, right? But I'm with you. I think there's so much positive with AI. Certainly a lot of danger around it too.
But of course.
Like anything, any technology comes with, both of those sides of the coin. Right?
Yeah. I think it boils down to how afraid are we of autonomy and kind of giving control to something else. And as you say, we can create our own heaven or hell with or without AI. I would say,
right? That's true.
Humans can do that.
We have been doing that for thousands of years already. So yeah,
exactly. So I think it's like like with autonomous cars, and there's been so much discussion, and we have those. I mean, in San Francisco, every second car is an autonomous car, and those are safe. Those are so much more safe. And of course, we've seen troubles with autonomous cars as well. There were accidents because of something wrong went with AI, but they are still much more safe than human drivers. And that's an example. You see it, you can touch it, you see that autonomy because you see the cars without driver. But in the mobile network, you don't see it, but it is there. So how much can we let go of control and see the benefits of it? Because humans are not perfect, unfortunately.
No, well, there's a really interesting story that I think relates to AI nicely, especially autonomous driving. Because when we first had elevators, it was terrifying prospect for people to get into a box and like pop off at a high floor, and we had elevator operators. There's somebody in there on a stool, like moving it up, moving it down, right? Yeah. And then, we started getting these systems where you could push a button and go to a floor, but they still had to keep the elevator operator in there because it made people freak out. Yeah. And then when we were trying to get the elevators operators out of there, the big thing that we had to add in that made people feel better was that big red stop button. So they could feel they could exercise some control, even though that probably they didn't exercise the best judgment in using those buttons. Still, to this day, I've noticed people don't use the proper judgment in exercising that. And I think that just speaks to the fact that we don't really have a good way of assessing, our risk. Because you mentioned, like, an autonomous vehicle may have a way better safety record than a human driving a vehicle. Mm-hmm. But still, that one time it malfunctions, which it's going to do more than one time, it's going to do it a lot. But at the rate, one of the most dangerous things that any human can do is get into a car and drive somewhere.
Yes,
because you're at the risk of everybody. So how do you, based on your, like what you talk about in your book, how do you shift that thinking to you read that one AI story, now you're like against autonomous vehicles, but they're actually maybe way safer. How do you reorient people's thinking to actually see the benefit rather than just always see the danger?
Yeah. I don't know. I think it's the only it's tricky,
Yeah, it
but
is.
we need to weigh the risks. I think that's the simple as that. I mean, kind of calculated risk, because as you say, like when you sit and drive in the car, that has a certain risk in itself, which is much higher than going in an airplane, right?
Yeah. Yes.
And then going into as autonomous car, what's that risk? So it's almost you can almost attach a little number with the risk to anything, to any action you do in the world. And then you kind of, okay, when you see the numbers, maybe we need to talk more about, risks in terms of numbers, because now we've had autonomous cars on the streets for a long time. Now we have the statistics, so you can see the risk. So we have all the statistics. I don't think, maybe not necessarily authorities want to show those risks, but they are there. The numbers are there. They're there.
Yeah, I guess it's a matter of like, getting people to understand data and putting it in a format so that people
Exactly.
can consume it. I think,
Absolutely.
I think we've lost a lot of trust in our society too, because, we've seen so many conflicting, statements about everything in the world, like that sort of sense of like, this is truth has
Yeah.
eroded over time in a time when we really, really need a sense of what is truth
Yeah,
now. Yeah. And I think
exactly.
AI does suffer from that, like you say, most of the books are painting a negative future. And
Yeah,
when
it's
you've got
popular.
that kind of perception that's being pushed on people, like really understanding the cost benefits of something gets a lot harder, I think.
Exactly, exactly. But yeah, as I said, it's fun to read a book about a catastrophic future. If
Is it
Why would I
fun?
read a book about bright future? I know. I mean, like this is like, but that the world is going under. That's interesting. Let's read about that.
Yeah, well, I mean, I guess we just need more people like you who are going to talk about the positive, future of AI. It's like,
We just need to show. I think it's like, yeah. I think after a while, when you kind of run with a certain level of autonomy, you can measure it. Maybe that helps. Put the number on it, like show the results.
yeah. I mean, you're right. I do think humans take time to adapt to new things and to start to
Yeah.
trust new things. We
Hmm.
trust through experience.
Yeah.
But unfortunately, AI is moving way
Faster.
faster than that. and
Yes.
it's only increasing, like I always talk about that sort of Malthusian, our ability to, adapt to
Yeah.
technology is kind of on a linear scale, whereas the rate of change and growth of AI is sort of on an exponential or logarithmic kind of
You're right. Yeah.
trajectory. And those points aren't intersecting anymore,
Yeah.
it's
Yeah. Maybe we
tough.
don't need to understand everything. I don't understand everything. I just trust some things.
Yeah, yeah. Well, but you're the AI expert, so we're going to be coming to you for what we should trust and what we
Explanation.
shouldn't trust, explanations and trust, right? It's funny. I feel like every time I talk to people who are thought leaders in AI like yourself, we always end up with the conversation waxing very philosophical.
Yeah. Yeah. Exactly. It's fun though. Sometimes.
Yes, sometimes. Well, when's the next edition of your book coming out? When should we expect that?
It's depends on our publisher, Springer Nature. So we'll see.
All right, all right. Well, keep an eye out. That it's Confessions of an AI Brain. And then if people wanted to, find you and find out more about Ericsson and the cool things that you're doing, where should they go?
Ericsson.com.
Ericsson.com. All right. And how
And
do you
then you can
spell that?
search
It's two R's, ERRI
Ericsson, double S.
double S.
Ericsson.
That's
Yeah. Yeah.
well, I'm hoping that's awesome.
With a
It's
C. Ericsson with a C.
ERICSSON.com.
Yes.
I've got it written
Yes,
down
that's
here.
correct.
Well, I really appreciate it. Thank you so much for, sharing all your insights about AI and all the new cool things that Ericsson's doing. 150-year-old company. My God, that's amazing that a 150-year-old company is now, pushing forward in AI, artificial intelligence.
Yeah.
That's,
Yeah.
I mean, could you imagine 150 years ago explaining to somebody what you would be doing now?
Yeah. No, not even 30 years ago.
Exactly. 30 years. I mean, like 30 years ago, cell phones were like, how does this work? Right.
Yeah, exactly.
And
Yeah,
you've already moved
yeah,
on, like 5 generations since then. So that's wild.
yeah.
Yeah.
That's cool.
Well, really appreciate it. Thanks so much for being on. And hopefully we'll, stay in touch and see where you go and, get your new book.
Thank you. Thank you so much. Thank you for having me.
You've been listening to IT Visionaries. Thank you so much for tuning in. And if you haven't already, be sure to hit that subscribe button so you get notified every time a new episode drops. And if you enjoyed this conversation, I know you will love my conversation with Christine Gadsby, Chief Security Officer at BlackBerry. Christine joined me recently to explore how AI, deepfakes, and weakened telecom infrastructure are reshaping the modern threat landscape. Check it out now in the show notes. Thanks again for tuning in. I'm Chris Brandt, and I will see you next time.